Comets are icy bodies of frozen gases, rocks, and dust that orbit the sun. They're perhaps most known for their bright, glowing appearances and the brilliant tails that trail after them. Some comets are famously bright enough to be seen with the naked eye, but most can only be seen through a telescope. Comets are generally very small. The ones that visit the inner solar system are generally only around 20 kilometers across, less than half the distance across New York City. It's quite impressive that these small things can make such brilliant displays. The word comet comes from the Greek word kometes, and I apologize if I pronounced that incorrectly, which means long-haired. This is in reference to the long tails of a comet. There are thousands of known comets, but there are thought to be billions more than what we know. They're just so small and dark that unless they're close to the sun, they can't be seen easily. Where do comets come from? How did they form? What's up with their tails? Let's take a look at the answers to these questions and more. A very long time ago, as in about 4.6 billion years ago, the solar system formed. It came from something called the solar nebula, a big spinning disk of material that eventually condensed into the sun, the planets, and pretty much everything else in the solar system. Comets might have been among the first solid bodies to form from this solar nebula. They came together in the outer regions, where it was cold enough for their volatile gases to condense and freeze. Volatile, by the way, just refers to a material that easily evaporates. Comets are very far from the planets, and because of this, they haven't experienced many of the same processes that changed the larger bodies of the solar system. They hold a sort of physical and chemical record of the solar nebula and the processes involved in the formation of a planetary system. These days, most comets orbit the sun in one of two regions: the Kuiper Belt and the Oort cloud. The Kuiper Belt is a region beyond the orbit of Neptune where objects like Pluto and Eris reside. The Oort cloud is much further out. Comets in or from the Kuiper Belt tend to orbit the sun in the same direction as the planets, and the plane of their orbits lies close to that of the planet's orbits. Oort cloud comets, on the other hand, tend not to orbit in the same direction as the planets, and their orbits can be tilted in very strange and extreme directions. Comets have been referred to as dirty snowballs because of their composition. It's a lot of dust, a lot of rock, and a lot of ice. There are 4 visible parts of a comet: the nucleus, the coma, the dust tail, and the ion tail. The nucleus is the solid core of a comet. It consists of frozen molecules including water, carbon monoxide, carbon dioxide, methane, and ammonia, as well as other organic and inorganic molecules. In other words, dust. The nucleus of a comet is usually around 6 miles across or less. The coma forms as a comet's orbit brings it closer to the sun. This close approach warms up the comet, and the ices on its surface begin to sublimate, or turn directly from a solid into a gas. This forms a very loose atmosphere, the coma, that is often up to 1,000 times larger than the nucleus. The dust tail is formed from particles of dust in the coma. Because these particles are mixed in with the frozen gases, they get released with them when they sublimate. Solar radiation pressure then pushes these particles into an elongated and curved path. The ion tail forms when the volatile gases become ionized by UV photons and are then blown away by solar wind. It points almost exactly away from the sun, and it often appears to glow blue because of the presence of carbon monoxide ions. Comets wind up in orbits that bring them close to the sun because of gravitational interactions. For ones that come from the Kuiper Belt, these interactions largely occur with the planets. But for ones from the Oort cloud, those interactions often occur with other stars instead. There are 2 main types of comets as classified by their orbits: the short-period comets, which are also called periodic comets, and the long-period comets. Short-period comets take less than 200 years to orbit the sun, and you can pretty reasonably predict when they will return. Long-period comets, on the other hand, are less predictable, and they can take millions of years to orbit the sun. Most comets travel a safe distance from the sun, but for some, called sun grazers, they fly so close to the sun that they either go right into it or they break up and evaporate. As they orbit the sun, especially on their close close approaches, comets leave a trail of debris behind them. If Earth passes through these trails, it leads to a meteor shower as these pieces of debris repeatedly burn up in the atmosphere. Comets are generally named after their discoverer, which has historically been a person, but in more recent years can also be a spacecraft. Some are named for the scientists that first recognized their orbits were periodic. The International Astronomical Union prefers a maximum of 2 discoverers credited in the name of a comet. In some cases, a comet was lost because its orbit was not determined well enough to predict when it would return. If it was then found again, it's named for both the original discoverer as well as the observer or observers who found it again. For most comet names, you will see a letter and a slash at the very beginning, and these letters mean something. C means it's a long period comet. P means it's a short period comet. D means the comet is deceased or destroyed. X refers to a comet with no known or meaningful orbit, and these ones tend to come from historical records. A is for an object that was originally classified as a comet but was then reclassified to a minor planet. A minor planet is basically anything that is not a planet or a comet. I is for objects with an interstellar origin, meaning they come from outside the solar system. Now, originally in the script, I wrote that there are currently only 2 of these, but literally just yesterday they announced that there could have been a third one discovered, so I guess there's 3 interstellar objects now. In 1995, the IAU implemented a new identification system. This system uses the year the comet was discovered, the half month in which it was found, which is represented with letters A through Y and excluding I, and a number showing the order in which that comet was found within that half month. So a comet with the ID of, say, 1985 D4 would be the 4th comet found in the second half of February of 1985. A number appearing before the name of a comet denotes a periodic comet. These are numbered in the order that they are determined to be periodic. Formerly, a number after the name of a periodic comet denoted the order among the comets discovered by that person or group. For example, the famous comet Shoemaker-Levy 9 was the 9th comet to be discovered by the Shoemaker and Levy group. But these days, new comets have no such distinguishing number. Humans have been seeing, observing, and recording comets for pretty much as long as we've existed. Chinese astronomers kept records of visible comets for centuries, and these have proven valuable for later astronomers. Early on, there were 2 kind of conflicting ideas about what comets actually were, with one coming from the Greek philosopher Aristotle and the other coming from the Roman philosopher Seneca. Aristotle thought comets were dry exhalations from the Earth, the planets, and stars that burned up in Earth's atmosphere. Seneca, on the other hand, thought that the comets were like the planets but on much larger orbits. Aristotle's view was the predominant one until 1577, when Danish astronomer Tycho Brahe attempted to use parallax to triangulate the distance to a bright comet. Because he could not measure a parallax, he concluded that the comet must be very far away, at least 4 times as far as the moon. In other words, it definitely wasn't in Earth's atmosphere. Brahe had a student, German astronomer Johannes Kepler. Kepler had devised 3 laws of planetary motion based on Brahe's observations of Mars. But he couldn't fit his theory to the very eccentric orbits of comets, and he believed that they traveled on straight lines through the solar system. Later, Isaac Newton used his new theory of gravity to calculate a parabolic orbit for a comet. Newton was friends with Edmund Halley, who used Newton's methods to calculate the orbits of 24 known comets. He published these in 1705. All of the orbits were fit with parabolas because the quality of the observations at the time just wasn't good enough to determine elliptical or hyperbolic orbits. In calculating these orbits, Halley noticed something. There were 3 comets, one in 1531, another in 1607, and yet another in 1682 that had remarkably similar orbits, and they all appeared around 76 years apart. So he suggested that these were all actually one comet that would return in 1758. And he was right. Halley didn't live to see it, but the comet returned as he predicted, and it was named in his honor. Halley's Comet, the first comet determined to be periodic. Though Halley could only calculate parabolic orbits, which would suggest that comets were not part of the solar system, he suggested that these orbits might actually be elliptical and closed instead. The second astronomer to recognize a periodic comet was German astronomer Johann Encke. The comet in question was discovered by French astronomer Jean-Louis Pons in 1818, and Encke determined that it did not follow a parabolic orbit. He showed that its orbit was a closed ellipse with a period of just 3.3 years, which is still the shortest orbital period of any comet on record. Encke also showed that the same comet was observed by French astronomer Pierre Méchain in 1786, British astronomer Caroline Herschel in 1795, and by Pons again in 1805. But the comet was named in Encke's honor because he determined it was periodic. But Encke's comet soon presented a new problem. Because it returns so frequently, it was pretty easy to observe it. However, it kept arriving about 2.5 hours too soon, which implied its orbit was shrinking. The problem was complicated even further when it was discovered that other periodic comets kept arriving too late. A purely gravitational orbit couldn't explain these abnormalities. Then German mathematician and astronomer Friedrich Bessel made a suggestion. The comets were expelling material near their perihelion, and this expulsion acted like a sort of rocket motor that propelled them into shorter or longer orbits. And he turned out to be right. Over time, observations and techniques improved, and it became obvious that most comets were on elliptical orbits and thus were members of the solar system. However, some orbit solutions for long-period comets were hyperbolic, which suggested that they came from outside the solar system. This was a problem that would not be resolved until the 20th century. In 1858, English portrait artist William Usherwood took the first photograph of a comet. Comet Donati, which was followed by American astronomer George Bond the next night. The first photographic discovery of a comet was made by American astronomer Edward Barnard in 1892. This comet became known as D/Barnard 3 because it was soon lost, but it was finally recovered in 2008 by Italian astronomer Andrea Boattini and is now known as Comet Barnard/Boattini. In 1864, Italian astronomer Giovanni Donati was the first to look at a comet through a spectroscope. The first comet spectrogram was of Comet Tibut, and it was taken by English astronomer William Huggins on June 24, 1881. Through the 20th century, a lot of progress was made in the field of cometary science, but there was still the lingering question of where long-period comets come from. There were three main schools of thought. First, comets were captured from interstellar space. This ran into serious problems because a capture by Jupiter, the most massive planet, was highly unlikely and couldn't account for the majority of short-period comets. In 1914, Swedish-born Danish astronomer Ellis Stromgren took the orbits of long-period comets and projected them back in time. By doing so, he showed that most apparently hyperbolic orbits became elliptical. This proved that comets, even long-period ones, were members of the solar system. Second, comets erupted from the giant planets. This was unlikely because the giant planets all have extremely high escape velocities, and no one could really understand what would give an object that escape velocity. And third, comets were primeval matter that had not been incorporated into the planets. This was the one that turned out to be closest to the truth. In 1948, Dutch astronomer Adrianus van Workum examined the role of Jupiter's gravity in the changing orbits of comets. He showed that Jupiter could sort of scatter these orbits, leading to shorter or longer orbital periods. In some cases, the perturbations from Jupiter were enough to change an elliptical orbit into a hyperbolic one, thus ejecting that comet from the solar system. Van Workum also showed that Jupiter would eventually eject all long-period comets from the solar system over a period of just 1 million years, which meant that these had to keep coming from somewhere. Van Workum's thesis advisor was Dutch astronomer Jan Oort, who became famous in the 1920s for his work on the structure and rotation of the Milky Way galaxy. Oort became interested in this problem of where long-period comets come from. He built on Van Workum's work and found a large number of comets have an orbit with a semi-major axis of over 20,000 astronomical units. From this, Oort suggested that these could only be explained if long-period comets came from that distance. He proposed that the solar system is surrounded by a sort of cloud of comets that extends halfway to the nearest star. This cloud of comets around the solar system was named in his honor and became known as the Oort cloud. In 1826, Austrian military officer and astronomer Wilhelm von Biela discovered a comet. This comet was calculated to have an orbital period of 6.75 years, and it was the third comet determined to be periodic. It was also identified with a comet observed by French astronomers Jacques Lebey-Montaigne and Charles Messier in 1772, and by Pons in 1805. As predicted, it returned in 1832. The same comet, called Biela's comet, was observed on schedule many times after. Then, on January 13th, 1846, American astronomer Matthew Maury looked for it, but he didn't find a single comet. Instead, there were two that followed each other closely around the sun. These comets returned again as a pair in 1852, but after that, they were never seen again. In 1872, a brilliant meteor shower appeared to come from the same direction from which those comets should have appeared. Astronomers concluded that this meteor shower was the result of debris of the disrupted comets. They were left with questions about why Biela's comet broke up. This recurring meteor shower is now known as the Andromedids, but they're sometimes called the Bielids. The study of meteor showers had received a massive boost decades earlier on November 12th and 13th, 1833. On these days, observers saw an incredible meteor shower with rates of hundreds or maybe even thousands of meteors per hour. This shower was the Leonids. It was suggested that Earth was encountering debris spread along the Earth-crossing orbits of some as-of-yet unknown bodies in the solar system. Further analysis showed that these orbits were highly eccentric. In the 1860s, American mathematician Hubert Newton published papers examining historical records of major Leonid meteor showers. He found they occurred about every 33 years. He predicted another major shower for November of 1866, which occurred. In the same year, Italian astronomer Giovanni Schiaparelli computed the orbit of the Perseid meteor shower, which is usually observed on August 10th to 12th each year. He noted a strong similarity to the orbit of comet Swift-Tuttle, which had been discovered in 1862. Soon after, the Leonids were shown to have a very similar orbit to comet Tempel-Tuttle, discovered in 1865. Since then, the parent comets of many meteoroid streams have been identified, but some remain a mystery. There have been multiple spacecraft sent to explore and examine comets. NASA's Deep Impact mission collided an impactor with comet Tempel-1 in 2005. The resulting explosion revealed the internal composition and structure of the comet's nucleus. The same mission also included a flyby of comet Hartley-2 and a remote sensing of comet Garrod during an extended mission. In 2009, NASA announced that samples returned from the comet Wild-2 during the Stardust mission revealed a building block of life, glycine. This was the first time an amino acid was found in a comet. In 2014, the European Space Agency's Rosetta spacecraft entered an orbit around the comet, I apologize for this, 67P/Churyumov-Gerasimenko. I tried. I really did. The Philae lander touched down on November 2nd, 2014. On September 30th, 2016, the Rosetta mission concluded when the spacecraft intentionally crash-landed on the comet. On June 19th, 2019, the ESA selected the Comet Interceptor mission as its newest FAST or F-class mission, and no, I don't know what that means. Comet Interceptor is due to launch in 2029, and it will, as its name implies, intercept and study a comet that actually hasn't even been discovered yet. Wow, there sure is a lot about comets, aren't there? These tiny little balls of rock and ice are surprisingly important to the solar system. I hope you enjoyed this video about comets. I would appreciate it, as always, if you could leave a like, and you can also subscribe if you'd like to see more. I'm not finished with Solar System Spotlight just yet. I'm getting there, but there's still at least one more video that I want to do first. Thanks again for watching. I don't think I said thanks before, but thanks again. Thank you again. Have a good day, and I'll see you next time.